And we can proceed to the last talk of today, which will be done by Aleš Smrčka, who is an assistant professor at one of the local universities, especially Brno University of Technology. He received his PhD in formal verification of hardware designs, but recently he's applying these experiences in formal verification in the area of testing and dynamic analysis. His research has a lot of area in testing and dynamic analysis, and he's going to present one of those today. Stage is yours.
Okay, hello again. My name is Aleš Smrčka. I love automating things. So that's why I'm doing this. Parametric log checking. I understand that this is the last talk. This is afternoon. Some of you might be tired, so too long didn't listen. Version for you is that we had a tool that can observe the sequences in the logs. We are looking for the sequences interleaved with other sequences of other programs, other services, and so on. Sequences might be tied together with parameters, so there might be different instances with their similar sequences. And if the sequences is witnessed in the log, we either are good with it, or we notify the user. But the longer version is that log checking is based on runtime verification. And because of the verification, it is somehow touched with the formal methods. But unfortunately, formal methods are good enough for us to prove that the system is correct. But runtime verification are closer to the software testing. And software testing cannot be used to show the presence of bugs, but never to show their absence, as Dijkstra said. So we have static analysis with formal verification and formal specification, and we have dynamic analysis, software testing, and runtime verification. The verification touches the formal methods with formal specification. We need the sequences to be formally specified. So dynamic analysis is based on experimental evaluation. We observe the trace, and we can answer the question, did we witness a bug in a set of different program runs? So all of you knows what software testing is, just to be sure. Software test or test case consists of 4 different phases. Set up the environment, exercise with the test inputs to the system under test or software under test, program under test, and so on. Then verify that the output from the SUT is as expected, and sometimes to tear down the environment and clear it up. The creation of test cases can be systematic or random. For example, it can be driven by the coverage criterion selected by you or your manager and so on, or the certification, for example. Random testing, let's call it, for example, fast testing, has been proven successful for example, security testing. So the testers create a number of different tests with those code beans, let's say, of these particular stages. So testers create different types of data, test inputs and test outputs. Let's call test outputs as the assertions, or let's call it set of post conditions, which should be checked after execution of the test. But testers like to think in what ifs. What if I'm lazy enough to create a number of test cases because I just want to generate or think about the test inputs, not also the test outputs or the post conditions. What if someone will provide me with, let's say, the function for the expected outputs with post conditions? Let's say that the function transform test input I will generate to the set of post conditions. So that way I can transfer the test cases into the simple simple steps. The first will be the setup of the environment. Let's say it is consistent. The generation of the test inputs, execution of the SUT, and after it I will call the expect function, magic expect function, to check for me the result. And another what if, I'm lazy enough to also create the test inputs. What if I use some random generator or test case generator, so that way I can enclose those 2 steps or those 3 steps into the loop. And the loop will be the fully automated test. In that case, I have a tool which can provide me with the bug hunting ultimate answer under which condition the system behaves correctly or incorrectly. I have 2 problems here. The first one is how to generate the inputs. But sometimes we know how to do that. We already have test input generators, or we can use the fast testing, for example. The second problem is much bigger problem. Who will provide me with the expect function, so-called expect function? There isn't someone. There is just you, unfortunately. And where does this expect function, if you want to program it, where do you get the information for that? From the SUT documentation and the specification. Unfortunately, except when you are working on high critical level application, there is, let's face it, there is no such thing as precise documentation. So we need to close the gap between developers and runtime verification of formal method practitioners, how to easily write formal specification. And moreover, we do not need the expect function to represent just the set of postconditions. We would rather want to have the properties which represent expected sequence of events in the SUT, let's say in the chronological order, for example. So, runtime verification is about the properties, and there are several different formulas how to express ourselves what properties are should be valid on the system or invalid on the system. There are extended irregular expressions, different state machines, even context-free grammar is used in the MOP, so-called well-known MOP runtime verification framework, or temporal logic. Well-known LTL or pasta LTL, metric temporal logic, and so on. We have a problem with so-called liveness properties, because liveness is important for potentially endless program. In that way, runtime verification cannot notify us about the violation of liveness during the execution, because we cannot say during the execution that, or we can decide if the system will eventually be back into an expected state. There are 2 different possible workarounds. Either way, it will be not infinite, so the system must react in a specific time limit, or we have an extension with the conclusion, with the verdicts, that it is not just true or false, but also the risk or pending, depending on if all future obligations are or are not fulfilled. So the simple runtime verification architecture as follows. We have specification. Let's say we have it. We synthesize from the specification the runtime monitors. Runtime monitors are some sort of code beans which monitors the sequences of events. Someone will be the test driver, which will generate the input for the system under test, for the test environment. System under test will be executed and will exhibit the sequence of events which will be monitored by our monitored synthesis. But this architecture is not so simple. These are more colorful. There are different classification, different problems. For example, we must decide what type of events we want to monitor, who will provide them. So the system under test or the test bed must be somehow extended to provide us with the internal states within. The monitor should be somehow inline or outline. That means the monitor is with these probes or code beans and somehow as one or are isolated. Runtime verification framework can be online or offline. That means that we are either runtime monitoring during the execution, or we are provided with the log or the sequence of events, and we may perform post-mortem analysis. So how to inject those code beans into the test bed or system under test? So there are different types of code injections, different techniques for code injection. Either we will change the code for the system under test, and nobody wants to do that. Or we will instrument it during the compilation, we will inject before the execution, or we will use the code interceptors during the runtime. Or we might have to use the separate program communicated with SUT. Let's say that it will be the tracers or log monitors or even profilers. Could be done, could be taken as the runtime monitor. So there is a tight line between two terms, runtime verification, and sometimes we hear about runtime monitoring. Runtime verification targets on the software under test. So we are testing before the production. Runtime verification can answer the question, does it behave correctly, does the system behave correctly under different conditions? Conditions which are even unknown in advance. Runtime monitoring, on the other hand, targets production system. That means that in the overall architecture, we do not have test environment and test input generator. We have real environment and real input. So we will also monitor potentially endless programs like network services, control systems, sensoring system, and so on. And runtime monitoring should answer us, does it still behave correctly in the production? And there are different verdicts or different actions if we witness some violation. For example, we want to notify the administrator, or we would like to switch during the runtime to partial operational or safe mode of the service, or we need to restart or include the self-healing of the system, or just fail the mission. So go back to the log checking. Log checking is specialization of runtime verification. That means that we do not need to change the code. We have a separate program. That means the runtime verification is outline. SUT generates even in logs, and the log checker reads and checks the logs. Log checking might be performed online or offline. It depends on you whether you run it. So that means it can analyze log as a stream, or it can analyze log as a file. And most importantly, we want to aim at easy specification, because the specification is one of the biggest problem in runtime verification. So let's say that there is no skill set in your team to create the perfect formal specification of the system. So we want to ask the developers what is the correct behavior of their system in a natural language. And developers do not want to talk in natural language. Developers want to talk in the programming language and the output of the program and so on. So once they introduce the SUT and inject during the development logging messages or even debugging messages into the program, they know exactly what those lines in logs means. So we have a log, the log of events, trace of events, and those events are somehow reveal the internal states of the running program. So we are asking the developers what those lines in the log really means, what are the internal states of the programs. And then we can transform it into the specification of the properties and just run our log checker. So we have two different types of properties, good versus bad properties. That means that good properties are the expected event sequences, or bad properties are unexpected. Good property means once the first event of the sequence occurs, the whole sequence must occur. The bad property means if a system of events as a whole is witnessed in the trace, we must report the violation of the property. So let's go to the example. Let's say we have a server with the Apache server, and let's say the Apache server is being automatically reloaded once someone will change the configuration. So we will look at the log to check whether there is a request for the reloading of the Apache server, and we need to be informed if subsequent reload failed. So we will create, we will have three different properties. The first one is the request for the reload. The second one is the witness of unsuccessful reload. And the third one is the witness of successful reload. So we will create a sequence of event, reload, not configured, and failed. And once those sequence is somehow witnessed, that means we need to get the notification about that. How does this work? So we specify the properties, log checker, extract the regular expressions of the log lines, and also regular expressions for the sequence of events. From the sequence of events, it creates the automata, and from the regular expression of lines, it extracts the set of filters for the logs. So the logs through the filters goes to the monitors, and monitors checks whether the sequence in the automata, whether a sequence are accepted with the automata. So we have our example, and once we run our log checker on this sample, we can get the witness or the violation of the property with different lines from the log checker, and also related or linked to the specific property which has been violated. But it is not enough for us, because consider the property that every file which is opened, then used, must be eventually closed. So we have opened, several times used, and then close. And as we know, these actions depends on the specific files. So these sequences are separated if we work on different files. So if we have a sequence open F1, use F1, use F1, open F2, and so on, there are two violations at that sequence, even though the work on F1 file is correct because it has been opened and it has been closed. So we need to take into account parameters, and in that way we extend our sequences with parameters. So each one of the events can have one or more parameters, and we will specify it and bound those parameters together. So events in a parameterized sequence share the parameter values. So we can have more parameters. For example, there is a property for unsafe update of a collection. Let's say that we have a collection, and once an iterator over a collection is created, it must not be used after collection update, because this is, for example, from the C++ standard. That means that all of the collection must not be updated while you are using the iterators. So you must get rid of the iterator once the update. So we need to extend our specification with the parameters. So there will be the lines extended with the parameters. You can see the section events over there. And also we will append the constraints, which somehow links those events with those parameters. So that's about that. So another example, let's say that the constraints should not be that the parameters must be equal, because we have the runtime verification. We can do whatever we want at that specific time, even to check if the parameters are somehow in some interval, for example. There might be different relations between those parameters. Let's say that we have the example of the attack to the SSH server. That means that some attacker from an IP wants to frequently try your username, for example, and you want to fail to ban those IPs. If, for example, in 10 seconds there were 3 different unsuccessful tries, you will ban those IPs. So I will create easiest property. So when there is a failed 3 or more times within the 10 seconds, please notify me about the sequence, and also notify me about the IP address, so I will want to ban them. So yeah, that's about that. So parameters, log checker with parameters works much harder. It needs to parse the constraints, and it needs to look for those constraints, and the monitor itself must take into account all of the parameters, which are unknown during the execution. You don't know which parameter will be in the next event. So the monitor will work as follows. Let's say we have a simple property, foo bar bus. Foo and bar event are connected with parameter O. Bar with bus are connected with parameter P. And let's say that we have a trace with the first line that the parameter O will have the number of 1. At that specific moment, we need to start the instantiation of the automata for the foo with parameter 1. In the line 3, you can see that there is foo with number 2. So that way, we will have 2 separate automata. Whoa, sorry about that. Where was that? Okay, so every time a new parameter appears, we need to take the record of that parameter, and also we need to take the record of the sequence of that. After we finish the sequence, we can decide whether we want to get rid of it from our storage, or if we want to just notify about that. So that is the limitation of the log checking. So at this moment we have the prototype tool. The prototype tool is command line tool. It is implemented in Golang. The reason for it is to be as portable as possible. So at this way we have the simple binary which can be copied anyway. It is a command line. It can stream the standard input for logs. And the simple example of the execution looks like this. It follows the automata with parameters, and it is inefficient because more unique values or their combination in the log means more memory consumption. This is the biggest problem of most of the parameterized runtime verification tools or frameworks. So there are different approaches how to do that, and one of the best is to implement garbage collector. So you are either safe, that means that all seen values are preserved, which is too consuming for memory, or unsafe, which means that you may miss some faults, but it can still somehow provide useful feedbacks for you, even in the long run. So we are applying at this moment plog checker in our Horizon 2020 European project in 2 different use cases. One of them is the use case when you are remotely controlling the car in the streets. So there must be different type of conditions on networks, and also different states within the remote station and the car and the gateway and so on. So we are helping the company to efficiently verify if their system is correct. We are helping them to specify the properties. We are helping them to create the YAML file for the plog checker. And once we are finished, they can do whatever they want. They can test whatever they want and let the plog checker verify their tests. Another example, it is just a toy example, this is not the best practice, is if you think, what if the log isn't the log from the system? What if the log is a textual representation of the trace of the system? Let's say that we have the strace program, which can somehow look into the internals of the programs, internals of the processes, and tell us which system calls are called. And we might, for example, check if some attacker could read the password from the root file, shadow file. Sorry, passwords from the shadow file. That means that the SUT should open the file, successfully open the file, and somewhere later should read at least 1 byte from that file. So we can also express that as the property for the runtime verification on the plog checker. And about the conclusion, runtime verification can improve your software testing with the automation of it or by expressing the test suite. Runtime verification complements formal verification, and I have a big respect for formal verification, but it can complement formal verification when it is computationally impossible to exhaustively verify, it is too expensive or time-consuming, or model assumptions do not meet the real systems. Log checking can relatively easy for log checking, it is relatively easy to specify the properties, even though they must be formally specified. Log checking, this means that there is a wider acceptance, possible wider acceptance of the method. Also, it is possible to make the analysis offline or post-mortem, and it can be used in production environment. But still, there is much work to make it universal. A lot of different ideas, a lot of different problems we must tackle. But we are not the only one. There's tens of years on runtime verification. Parameter itself is like 10 years ago, and there are different tools to make it with optimized garbage collector, with optimized trace events, and so on. And maybe just a note at the end, during this summer, the runtime verification engine has been included into the kernel, Linux kernel. So this will be, as far as I know, this will be published as the version 6, I believe. And it is not parametric. It is just for the runtime verification of the sequence of events in the Linux kernel. But it is efficient. Looking for the events is with the constant complexity. And that's all from my side. Thank you.
Thank you. Maybe a notice on the beginning. The runtime verification engine that you mentioned was implemented by Red Hatter Daniel Bristott. So yeah, just to mention that. We have a lot of questions, but fortunately we're quite ahead of time, so hopefully we'll go through all of them. So the first one. Have you got any tips or insights on how to do application logging better based on your expertise in log checking?
What to do better?
If you have any tips how to improve application logging inside the application based on the insights from your work.
Yeah, no. Start with the beginning of coding. Log everything. Yeah, log everything and think about different verbosity level. That's all. Yeah.
Okay, thanks. The second question from Ivan Nechas. Do I understand correctly that the parameterized sequences need to be specified manually? Can data from the tests with known results be used for training the sequences?
Yeah. Interesting question. To be honest, I don't know. Yeah, as far as I know, parameters must be done manually. But yeah, this is the interesting section. Interesting question. I should enlist those in the future work. Thanks.
Okay. What kind of errors can we express with your properties? Can we specify and check, for instance, concurrency-related errors?
Yeah. We can specify concurrency-related errors, but there is one thing which is very specific for concurrency. At this specification of the sequence, we think about the chronological or logic order of the sequences. We do not think about that any sequence might be interleaved with any other sequence. So we may specify it, but the specification would be much bigger because it should count with any interleavings in that.
Thanks. You actually just replied to another question which we had, which is very nice. Yeah, the famous question. What about false positives and false negatives?
There shouldn't be false positive, because once we are witnessing something, it is an error, because we specify it as an error, and it is as an error. We may miss something. That means if we garbage collect some of the open sequence, we may miss them. Yeah. So that's about that.
Okay, thanks. Another question, there's a service called Sentry.io, which is doing log checking and traceback reporting for our application. Is it similar to your log checker?
Yeah, as far as I know, yes. Yeah, and this is the only answer I can get. Yeah.
Okay, thank you.
It rings a bell. The name for me, I heard about that, and know it is somehow related, but sorry, I don't know how.
Okay. Another question is, can we use runtime verification for tests where we expect that some of the tests will fail? For instance, one failed run from 1,000 is okay? Can you use runtime verification for such a case?
At this moment, I don't think so. Because the quantification of the test cases, of the quantification of the logs isn't implemented yet.
Okay. Yeah. Another question. Parametric log checking is technology agnostic and basically works on the top of text data stream. That's more like a question if the questioner
definitely yes.
understands correctly. Okay.
Anything which is textual based can be seen as a log if you sort it.
Yeah, makes sense. What were the main challenges when you deployed the system to production?
Once more, please.
What were the main challenges when deploying the system to production?
Main challenges, garbage collecting. Because the garbage collector slows down the analysis of the logs a lot. So the main challenge is how to create the internal data structures, preserving all of the open parameters, all of the open sequences.
Okay, this is an interesting question related to the cloud environments. So can you track a bug propagation through multi-service system under test, such as microservice architecture or SOA, when bug might originate in a different component?
At this moment, no, and it is one of the bullets, still much work to make universal.
Okay, another question, is there a way to automatically prevent misdetections? For example, in the OpenShadow example, what happens if the file descriptor 3 gets closed and opened as something else? So you basically reuse the file descriptor in between.
Yeah. For example, between open and read, yellow and green line, if the file is closed and opened again, another file with the same file descriptor, or for example, the file descriptor will be duplicated and rewritten by another different, we need to enhance the property there. So yeah, this property can provide false positive, but a false positive of what we want instead of what we written. What we have written, yeah.
Mm-hmm. Okay. And last question, is there any default limit for the sequence searching area?
Default limit? As far as I know, it depends on implementation. Our implementation, for example, is based on different tables, and we have the limits for the tables. One table means each of the records in the table means one parameter in the one parameter of the event, and we have the limit of the table. So once we reach the boundary, we start garbage collecting and search for possible victims.
Okay, thank you. That was all from the questions.
One more?
One more.
Just to maybe be more precise with the question. So, yeah, back to the example, thank you. So, it seems to me that writing manually these
properties
is quite prone to errors, such as this one. So, is there a way to automatically somehow prevent such errors?
Sorry, for the recording, I will repeat the question. The question was that it seems that it is easy to, or it can be hard to specify the properties correctly and to write properties in such a way that the false positives may occur. Is there an automatic way to prevent something like that happening?
As far as I know, no. Yeah. Because once a human tries something right into the file, this is not error prone. Yeah. And you're transforming natural language specification into the formal language. And to maybe conclude with this, I started with the formal verification, and I discussed with developers about the properties, about the behaviors, and so on. So I was the one who write formal specification in LTR or CTL logic. Even though subsequent model checking tells me that the system is okay, I did not believe myself, even though I have several years of expertise in that. But there are different approaches how to do that. For example, automatically check if the property is realizable, for example. Yeah.
Okay, thank you. That's all. Thank you for answering all the questions. Let's thank the speaker again.